interpolation and stuff. And I think I might be able to grip the chalk normally today, but maybe not. I'm not sure. We'll see. So we're talking about the DTFT, and we went through the whole thing about operational rules. And the only ones I talked about were the time shift rule and the convolution rule for DTFTs. And we talked about the DTFT as a frequency response for an LTI system that has a frequency response. So I'll just title that as DTFT and LTI systems. And of course, the LTI systems we're talking about here are discrete time systems as opposed to continuous time systems, which we deal with the Fourier transform with. And at the end of class last time, I started talking about the sampling and interpolation stuff. So we started the sampling / interpolation stuff. And we're going to get through a lot of that today. I told you I'm not going to do the spiel about the movies. You can watch that on the old video note from fall 2011 because most of you have seen that, me talking about the movies and the wheels turning. We'll get back to that at the end of this discussion. But anyway, if you're given a continuous time signal, x sub c, and we're always going to use the subscript little c to indicate you're talking about a continuous time system, and we're going to assume all the signals are complex valued. So just right off the bat, just say xc in c to the r, and some t bigger than 0, you can form a signal just plain x, and this is going to be in c to the z by means of the following prescription. X of n is equal to x sub c of nt for all n. And this is just t sampling x sub c to give you x of n. So the picture looks like this. X sub c goes into this thing that I call a t sampler, and out pops x. And that's a linear operation on signals. And it's surjective as a mapping from c to the r to c to the z, but not injective in the sense that you can interpolate between any discrete time signal's values to get a continuous time signal for which that discrete time signal is the t-sampled version. But there are many ways of doing that. So it's not an injective mapping continuous time signals to discrete time signals. And here's a question. So, question. In this context, suppose that x has a DTFT. And that won't necessarily be true. There are examples in the monograph where you have a continuous time signal, and you sample it, you get a discrete time signal that doesn't have a DTFT. X hat is the DTFT of x. How is x hat related to the continuous time Fourier transform of the continuous time signal xc? So that's x hat sub c. And the answer comes from this thing I call the deconstruction equation. Which is kind of a joke about literary theory. You don't have to know anything about literary theory. You don't have to know why it's a joke. That won't be on the test, whatever. But anyway, here's a fact. I call this the deconstruction equation. It turns out that x hat of little omega is equal to the sum from k equals minus infinity to infinity of 1 over t xc hat of little omega over t plus k 2 pi over t for all omega. And this I call equation D. And there's a proof of that in the monograph. It's not difficult, but it's not worth doing in class because it's really just shifting variables and integrals and all that. And at the very end of class, I was talking about implementing this equation. And this will illustrate some important concepts. So you can implement this equation D in 2 steps. First one is you form what I call f, and this is going to be a function of capital omega, by means of this. F of omega is equal to the sum from k equals minus infinity to infinity of xc hat of capital omega plus k 2 pi over t for all omega in the reals. So what you do is you take the continuous time Fourier transform of the continuous time signal x sub c, you look at all of its translates by 2 pi over t, integer multiples thereof, and you add those all together. From f, you get x hat simply by rescaling f both in amplitude and argument. So rescale to get x hat from f. X hat of little omega is equal to the sum over k of 1 over t. Well, in the middle I'll put just 1 over t, f of omega over t equals the sum over k of 1 over t, xc hat, little omega over t plus k 2 pi over t. So you take that f and you rescale it in amplitude by 1 over t and in argument by 1 over t, or by t if you wish. Okay, now let's draw the pictures. Let's draw some important pictures. And by the way, important comment here. I made it last time, but I'll make it again. You need not assume that x sub c is a band-limited signal for this equation d to hold. So d holds even when x sub c isn't band-limited, provided the discrete time signal x has a DTFT. Even though the majority of applications we're ever going to look at concern band-limited continuous time signals that we sample in this way, this equation holds essentially under all circumstances. Okay. All right, here's some pictures to show what's going on. Suppose xc hat looks like this. It's a easy to work with picture, just a triangle like so, and say it goes out to plus and minus omega m. And maybe let's call these omega m stars. How about that? Just because. So the signal xc in this case is band limited, and its bandwidth is omega m star. Okay. Let's form f. So first you form f. To do that, you take all the 2 pi over t shifts of that picture and add them all together. Two different things, one of which will happen, the other of which won't happen. So two things can happen. Thing number one is this. F of omega looks like this. So what's this? This is going to be 2 pi over t, 4 pi over t, 6 pi over t, and the same thing happening over here. So this is minus 2 pi over t, minus 4 pi over t, and so on. Okay? And so pi over t is going to be right in here. The assumption implicit in drawing this picture is what? And I asked you that last time, and I think you were the one who said what it was. So let me ask it again. What implicit assumption am I making in drawing that picture, Erica?
That the widths are kind of overlap over that.
Yeah, exactly. And to state that precisely, see, this is omega m star, right? That's the bandwidth of x. So this picture assumes that omega m star is less than pi over t. And another way of writing that, I don't know why you would want to do this, but you'll see later on, is that 2 pi over t is bigger than twice omega m star. Yes, now you're seeing it. You're seeing it come. You're remembering something from EC 2200, eh? Yep. Okay. All right. What's the other thing that can happen? The other thing that can happen is that adjacent shifted replicas of xc hat actually collide in omega space. So this is the other thing that can happen. You get something like this. So this is 2 pi over t, and this is pi over t. Same thing's happening over here. It's minus 2 pi, and minus pi over t, minus 2 pi over t, and so on. In this case, that inequality is reversed. Omega m star is bigger than pi over t. So 2 pi over t is less than twice omega m star. That's what that picture assumes. And the terminology associated with this picture, which we'll get into more later on, for the second picture, we say that, quote unquote, aliasing occurs in this case. And why people call it that, we'll get to that later on. Whereas no aliasing occurs in the other case. Okay. Okay, so those are two things that can happen. Now, once we formed F, we form x hat, the DTFT of the discrete time signal x, just by rescaling F in amplitude and frequency. So the pictures are going to look exactly the same, except maybe squashed in and raised up or whatever. So then you form from F, form x hat by means of the description x hat of little omega is equal to 1 over t x, or f hat, or f of little omega over t. So this is what, in the first case, the no aliasing case, this is what x hat is going to look like as a function of little omega. It's going to look just like that picture up there, except the heights of these triangles are going to be scaled by 1 over t. So if, say, the height of that was 1, then these would be 1 over t high. I'm not going to be so worried about the height. But instead of having 2 pi over t there, you have 2 pi. And instead of having pi over t there, you have pi. And you have minus pi over here. And so on. Because you rescale the frequency variable. Now let's look at what happens in this no aliasing case. If you just look at the interval from minus pi to pi, the DTFT of x, the discrete time signal, looks just like a scaled version, scaled in both time and amplitude, of the continuous time Fourier transform x hat. So the key observation in this no aliasing case So observation in this case, little x hat, or x hat of little omega is equal to 1 over t, x c hat of little omega over t for values of little omega between minus pi and pi. And if you just flip that around, you can write it this way. You can say that xc hat of omega, capital Omega, is equal to t x hat of capital omega t when capital Omega is in between pi over t and pi over t. These are the same thing. These are exactly the same thing, just written as functions of different omega variables. And in this case, we already know, so moreover, in this case, we know already that xc hat of omega is equal to 0 when capital Omega is bigger than pi over t. How come? Why do we know that? Well, look at the picture up there. Pi over t is outside the bandwidth of xc hat. Of xc hat because of that. Thus, for all capital Omega, xc hat of omega is equal to this. It's equal to t x hat of omega t when omega is less than or equal to pi over t, and 0 when omega is bigger than pi over t. Now, why is this a profound thing? The profound thing is that the discrete time signal x, which is a sampled version of xc, completely determines x hat, its dtft, and that dtft by this equation completely determines xc hat, which in turn completely determines xc. What does that mean? That means you can figure out xc from its sampled version x. In this case. Okay, so let me phrase it in a way that puts it all together. And I'm going to call this version 1 of the Shannon-Nyquist Sampling Theorem. And then I'll rhapsodize about this Shannon-Nyquist Sampling Theorem for 2 minutes. And you'll have to pardon me. So let's summarize as follows. So this is the Shannon-Nyquist Sampling Theorem, version 1. We're going to have 2 versions. In past instantiations of this course, I've had up to 4, but I think 2 is enough, basically. Suppose xc, continuous time signal, complex valued continuous time signal, has bandwidth, is band limited, and has bandwidth omega m star. If capital T bigger than 0 is small enough so that two pi over t is bigger than twice omega m star. And the reason I'm writing it this way, if it's not clear to you already, will become clear momentarily. And notice if I ratchet down t, sooner or later t's got to be small enough so this inequality holds. Then you can, in principle, recover the entire continuous time signal xc from the discrete time signal x, and so x is going to be in c to the z, defined by x of n equals x sub c of n times capital T for all n. Okay, now what's the colloquial version of this? Quote, if you, and I'll write down the one-line proof in a moment, if you sample a band-limited signal at a frequency greater than twice the bandwidth of the signal, you can reconstruct the signal from those samples, at least in principle. And that's the sort of the whole plaza version of this version 1 Shannon-Nyquist sampling theorem. This is the kind of thing that everybody knows, even hoteliers. You know. Actually, it's not unprecedented to have hotel students transfer into engineering, after which they learn this. Now, where does this twice the bandwidth sample fit? The thing is, this frequency here, 2 pi over t, that is the angular sampling frequency. And having that be bigger than twice the bandwidth is the criterion to make this theorem true. Now, what's the one-line proof based on what we know so far? Here's the proof. X, the discrete time signal, determines x hat, that's just the dt ft of x, in turn x hat determines xc hat by means of that equation that we had before that relates them. Xc hat of omega equals Tx hat of capital omega T when omega is in between pi over T and minus pi over T and 0 when omega is outside of there. And xc hat, in turn, determines xc. By means of equation script f inverse. Because if you know the continuous time Fourier transform, sometimes you can't plug it into that equation, but just say you can. If you can, it still determines the signal, xc. David?
I had a question about why it needed to be like piecewise for the xc term. So when we defined x hat c, right?
Yeah.
We set it so that it only is, it needs to be 2 pi periodic to use the inverse one, right?
Okay. What's 2 pi periodic? This is 2 pi periodic. X hat, the dTFT of the sampled signal,
Right.
that is 2 pi periodic. XC hat is not 2 pi periodic. XC is band limited, so it's
It's just one, right?
well, no, hang on a sec. XC, the signal XC is band limited, so its Fourier transform has to be 0 outside of some interval. And that's about as far as from 2 pi periodic as you can get. And that's why we have to two-part it. That's why we have to do two specs. Because this thing here is 2 pi periodic. It goes all the way out in capital omega space. And the only part of it we care about is between plus and minus pi over t.
Okay, and what about keeping it within in that interval is helpful for the inverse transform?
Well, it's not a matter of being helpful. It's a matter of this is a specification of xc hat of capital omega for all omega. Okay? And it's true. It's not that it's helpful. It's just that it's true. In the case where you don't have collisions, those two relationships hold, but only in that interval.
Right.
Got it?
Yeah.
Okay. See, this is the advantage of having 3 board panels, that still exists. It hasn't been clouded over. So that's the proof. That's it. End of proof. Okay, now yeah. Will.
About the term bandwidth.
Yes.
Does that mean that the frequency content goes between minus omega m star to omega m star, or minus omega m star over 2 omega m star over 2?
In this class, it means minus omega m star to omega m star.
Okay.
Yeah. Yeah, the way we defined bandwidth was the inf of all the omega m's such that x hat is 0 for omega outside of omega m on either side. So that's, and if you take like digital communications or something, they might define the bandwidth differently. It's always by a factor of 2 though. All right. Okay, so now the rhapsodic thing I have to apologize for. Who was Shannon? Shannon was a mathematician who spent most of his career at Bell Labs, which was the last great industrial lab on Earth before Microsoft Research, I guess. Xerox PARC, whatever. My dad worked there. My grandfathers both worked there. How about that? Anyway, and Shannon was there, and Nyquist was also there earlier than Shannon. And Nyquist is more known for his work in control systems and stuff. But their names are both attached to this theorem, even though in some places you'll see it called Shannon Sampling Theorem, and other places you'll see it called Nyquist Sampling Theorem, whatever. And it really is hugely, wonderfully important result. And we had a survey back about 15 years ago when the old building manager retired in Phillips Hall. And he surveyed the EC faculty and said, please vote on what you think is the most important thing that's come out of electrical and computer engineering ever. Okay? So you can think of a few things, like the transistor, that might be important, right? The chip, that might be important. But believe it or not, who won that poll was the sampling theorem. A theorem won the poll. That's pretty wild. Why is it so important? Everything we do, all communications nowadays, is based on this. All music reproduction is based on this. Movies, cameras, everything is based on this. If you didn't have this theorem, you wouldn't be able to do what we do. Okay? Any kind of DSP. So there, it's huge. And anyway, I don't know. I don't know what else to say. I like the theorem. I like the theorem. Okay. It's dope. Okay. It's the bomb. No. That's like mid-90s, right? No one says that anymore, right? Is that correct? Anyone say? Because I saw someone said that on Facebook yesterday in someone's about somebody. One of my ECE friends said it about another one of my ECE friends. So that's why I saw it. It's not like I'm Facebook stalking everybody. He said, she said, you da bomb to somebody. Okay, so she was probably kidding around. What's that?
I think you need new friends.
I know that's true, but
Maybe some more modern people say the bomb.com.
oh. What about the bomb.edu? Is that Harvard? The bomb.org? What would that be? Okay. Now, all I've said here, all I've said is that you can, in principle, recover XC from the samples. I haven't given you a formula that gives you XC in terms of the samples, and that would really be nice, you know. So we ought to be able to give formulas, in this case, and we actually do. We have nice formulas giving XC in terms of X, its sampled version. Formula number one comes by just plugging this expression for XC hat into equation script F inverse. So one such formula you plug that last expression for XC hat into equation script F inverse, and you get the following. You get XC of t equals integral, or 1 over 2 pi actually, integral from minus pi over t to pi over t, t x hat of omega t e to the j omega little t d omega for all t, all little t. And when you say this formula out, you know, if you're saying it to someone who can't see for whatever reason, doesn't have their glasses on, can't see, period, you have to make sure you say that there's different t's in there. Okay, there's a capital T and there's a little t. Now, why is this a formula giving XC in terms of X? Well, X hat is implicitly in terms of little x. So that's why this is a formula for XC in terms of its sampled version, little x. Okay, that's one formula. Another formula is even more explicit in a certain sense. Because it spells out exactly how the samples in X build up the signal XC. So what we do is we take that X hat and we explicitly render it in terms of discrete time signal X. So another more explicit formula comes from first writing x hat of capital omega, or x hat of little omega, equals the sum from k equals minus infinity to infinity, x of n e to the minus j n omega for all little omega. which means that t x hat of capital omega T is equal to the sum from k equals minus infinity to infinity t x of n e to the minus j n capital omega T for all capital omega in the reals, which means that when I plug this under the integral sign and integrate, to get xc of t, I get 1 over 2 pi, that's t over 2 pi, integral from minus pi over t to pi over t, the sum over k, x of n, e to the minus j n omega capital T, all that times e to the j omega little t d omega. And assuming you can, the sum converges nicely, you can interchange the summation and the integral. And you get this. Sum over k. I don't know why I'm going through this. Or sum over n. There should be n here, right? All these should be sum over n. I'm so used to doing sums over k. There. Those are all sums over n. Thank you for whoever was making irritated noises. Alex. No, it wasn't you. Is over here? It was Sachet. You were making irritated noises. That's a good thing. It's a good thing. Yeah. Now, what if I turn around and said it was a bad thing? No. Then it was you? Okay. T over 2 pi, integral from minus pi over t to pi over t. And you can collapse and you can put an x of n here in front of this. And the integral is going to be e to the minus j capital omega little t minus nt. Or just positive, that's positive, d omega. And if you integrate this out, it comes out really nice. That integral becomes 2j sine of the argument after the j. Things cancel, things move around. And you get this. And this is supposed to be for all t in the reals as well. That's a t. So integrate it out, and you get this. X sub c of t is equal to the sum over all n, x of n times sine pi over t times t minus n cap t divided by pi over t times t minus n cap t for all t. And that is an explicit expression for the continuous time signal x in terms of its samples. These are the values of x sub c at time nt for every n. And the things that they multiply are shifted sync pulses, right? Signed thing over thing, that's a sync. And if you look at where the zero crossings here are, they're all in the perfect position so that x of n comes out to be x sub c of nt. Everything works out nicely. David?
So this technically means that you need every single discrete value to get one
Yes.
continuous time value.
Well, to get all the continuous time values. To get the continuous time value at time 0, all you need is the discrete time value at time 0. But to get the continuous time values for all t, you need all the samples.
Okay.
And that's the in principle part of the Shannon-Nyquist sampling theorem that I just erased.
But if you plug in 0, there's still a infinite sum. Like if you plug in 0 for t to try to find x c is 0, you still have an infinite sum.
But the sig term is only non-zero for one particle constellation.
Oh, right. Okay.
If you plug in t equals 0, what happens? You have a bunch of sine n's over n's, all of which are 0 except for n equals 0, as Ian just pointed out. All right. So what does this say? This shows that you can think of xc arising, xc, as a what one might call a sinc function interpolation of its samples. And this, of course, is all predicated on the assumption that xc is band limited and t is small enough so that 2 pi over t is bigger than twice the bandwidth. Okay, so this is one kind of interpolation. Anyway, that's a nice representation of x sub c in this case. All right. Now, question. Like, there's an equation up there for xc. There's another equation for xc in terms of the discrete time signal x. You can think of either of these representations of xc as coming from, arising from, a sort of a box, a system that processes x. So x goes into this system, and out comes xc. Okay? What is the system? You can call it anything you want. I'm going to call it a sinc function T interpolator. Okay? Question, what if x does not come from sampling a continuous time signal x sub c faster than twice its bandwidth? What if x is any old discrete time signal? It could just come out of nowhere, or it could be from sampling a band-limited signal slower than twice its bandwidth, or it can come from sampling a non-band-limited signal, whatever. You have this box. You could plug any such x into such a box, and something's going to come out. Okay? So that's the question I want to address now. Actually, now's a good time to take the 3-minute break, so let's do that. And by the way, I didn't bring the prelims, and I didn't bring the graded homework. So there. X going into the sinc function T interpolator and xc coming out holds only. So the picture assumes the conditions of the sampling theorem. That is to say that x sub c is omega m star band limited, and x of n is equal to x sub c of nt for all n, with 2 pi over t bigger than twice the bandwidth of xc. But, you know, if you walk into a lab and you find a sinc function T interpolator laying around, right? You know, it's clear that it takes discrete time signal and puts out a continuous time signal. What if you just took any garden variety discrete time signal, x, and put it through a sinc function t interpolator? What's going to come out? Okay, so suppose not. That is to say, suppose you just start with any old discrete time signal x, so x is going to be in c to the z, and you might as well assume it's reasonably well behaved, like it has a DTFT. So assume at least it has a DTFT. You take any old discrete time signal and you use it as an input to the sinc function t interpolator. Question is, what comes out? Let's call what comes out x sub r. It's a continuous time signal. So call the output signal x sub capital R. And I always have to look up in the monograph whether I use capital R or small r, and I just looked it up during the break and I use capital R, so I can close the computer now. Here's two expressions for x sub r. And I'm going to give these names. This one I'm going to call equation capital R1. It says x sub r of t equals 1 over 2 pi integral from minus pi over t to pi over t t x hat of omega cap t e to the j omega t d omega for all t. And this capital X hat comes from taking the DTFT of whatever the garden variety input signal little x is that you put in. And the other expression is going to be that infinite series of sinks. And that I'll call equation R2. X R of t is the sum over n, x of n, sine pi over cap t, t minus nt divided by pi over t, t minus nt. Okay. All right. Two properties of x sub r that are pretty easy to know. First off, if you think of equation R1 as representing equation script f inverse for the signal xr, you see that the continuous time Fourier transform of xr dies outside of plus and minus pi over t. So xr, the signal that comes out, is band limited to within pi over t. And the reason is R1 reveals that xr hat of omega equals 0 when omega is bigger than pi over t. Okay? You can just think of equation R1 as equation script f inverse for xr. Second property, the continuous time signal xr actually does interpolate the signal x. So xr, quote unquote, t interpolates x in the sense that x of n equals x sub r of n times capital T for all n. Why is that true? That follows directly from equation R2. So because R2, I'll just say, that was painful. Still a broken thumb, so it's hard to, you might not even know because you haven't been around for a while, but no. That's okay. No, I'm not knocking that. I'm just saying, wow, it's cool that Ricardo does so well and he never goes to class. It's like anyway, because R2. Let's just leave it at that. Why is that? Why does R2 reveal that XRT interpolates between the samples? The idea is that if you want to see the proof? Let's just do it anyway. So say you want, well, no, just plug in t equals little m times capital T into R2, and you get this. You get x sub capital R of mt is the sum over n of x of n sine pi over t, t minus, it's going to be mt minus nt divided by pi over t, mt minus nt. And that's the sum over n, x of n, sine of m minus n pi divided by m minus n pi. And this is like we were talking about a few minutes ago. Every term in this sum is 0 except for when m equals n, or n equals m is a better way to say it, where you get sine 0 over 0, which is 1. So that's true for all n. All right, so XR, the signal that comes out of the box, when we plug in garden variety discrete time signal x that has a DTFT x hat into the box as an input, the signal that comes out has two properties. Property number 1, it's band limited to within pi over t. Property number 2, it interpolates the samples. That leads to version 2 of the Shannon-Nyquist Sampling Theorem. And this, in some sense, is the cooler mathematical way of stating it. Or the mathematically cooler way of stating it. So Shannon-Nyquist Sampling Theorem, version 2. Goes like this. If x in c to the z is a discrete time signal that has a DTFT, then let's give it the name x hat. There's exactly one continuous time signal Oh, well, let me state this better. For every t bigger than 0, there's exactly one continuous time signal x sub r, let's call it, because it's going to be this x sub r, with the following two properties. Property number 1, it's band limited within pi over t. Property number 2, it interpolates the samples. So with properties 1 and 2, i.e. x sub r hat of capital omega is 0 when omega is bigger than pi over t, and x sub r of nt equals x of n for all n. So the theorem says that among all the myriad ways of interpolating the samples, or interpolating the values of this given discrete time signal x, there's only one way to do it, t interpolating them, there's only one way to do it and to get a signal that's band limited within pi over t. That's another way of looking at this theorem. Okay, why is this true? We know from equations R1 and R2 that the x sub r that we get from those equations has those two properties. So there is at least one way of doing it. Why is that the only way to do it? It's the only way to do it because of version 1 of the Shannon-Nyquist sampling theorem, essentially. That if you take that x sub r and it's already band limited to within pi over t and you sample it every t, that means you get x. Okay, so am I talking in circles? Does that sound circular to you guys? Yeah, it does. Okay, well, let's look at this more carefully. So the idea here is that if you start with a discrete time signal x, you don't even know where it came from. It could have come in the mail. It could have come RSA encrypted, whatever. And you plug it in, or no, if you start with that discrete time signal, you can think of all the different ways of interpolating it. There's lots of ways of interpolating it, right? So the reason to see this, so equations R1, or equivalently R2, yields a signal that has those two properties. Question: what if there were another signal that had those properties? Let's call it y, yc. So say yc is another signal that has those properties. What we want to show is that yc is the same as x sub r. How do we do that? If we take yc and put it through a t sampler, what do we get? What discrete time signal do we get? Who said that? X, you're right. Because yc interpolates the samples. That's property 1. So because 2. It's actually property 2. Now, what if we put that x through the sinc function interpolator? What comes out? X sub r. And that has to be y. Now, wait. Now I'm losing it myself. So let me just think a second here. I think I rhapsodized too long on the Shannon-Nyquist sampling theorem. Lost the thread. So let me try to pick it up again. Oh no, wait. We know this is x sub r, but it also has to be y. So this is by definition of x sub r. But why does it also have to be yc? Because what? Because yc has property 1. Property 1 plus version 1 of the theorem. That if I take a signal, yc, that happens to be band limited between pi over t and minus pi over t, to within pi over t, in other words, and I sample it faster than twice that bandwidth, and plug it into a sinc function interpolator, yc comes out. Conclusion, yc has to be x sub r. So yc can't be another signal. Denzel, does that clear it up a little bit? I agree with you that I was sounding circular a minute ago. Feeling circular. My narrative arc was closing in on itself. Snake eating tail, whatever analogies you want to do. Okay, so this is the Shannon-Nyquist sampling theorem, versions 1 and 2. And let me just scribble down the colloquial version of version 2, colloquial rendering of version 2. So colloquial rendering of version 2 goes something like this. Among all the ways to quote unquote connect the dots in X to yield a continuous time signal, there's only one way to connect them that yields a signal, band limited, connect the dots to like every t to get a continuous time signal from that. There's only one way to do that that yields a signal that's band limited to within pi over t. It's one special way of connecting the dots. All the other ones aren't band limited to within pi over t. So there's, in some sense, there's a, given a capital T, there's a special way of T interpolating any discrete time signal x. And that's this sinc function interpolation. So here's another way. Given x and t, there's a sort of a preferred or special or preferred or lowest bandwidth way of T interpolating X. Okay, fair enough. And that's the one that comes out of the sinc function interpolator, X sub r. Okay, now let's think about the movies again. Okay, we didn't talk about it this semester, like I said, because I talked about it before. But what's happening when you watch a movie, roughly speaking? Roughly speaking, what's happening is the following. You're seeing a bunch of still photos flashing on the screen. One every 1/24th of a second. Standard Hollywood frame speed. You pass those through your eyes, through the visual apparatus of your brain, whatever, and you build a continuous time signal in your head. Okay? So watching a movie is like T interpolating. Roughly speaking, it's like T interpolating the frames that represent the discrete time signal x with t equals 1/24th of a second. Okay? So roughly speaking, that's what you're doing when you're watching a movie. Now, you and you and you and you, we all have different brains. We all have different bodies. We all have different visual systems, whatever, although we are all probably quantum connected and entangled in some bizarre way, you know. But we don't T-interpolate in vastly different ways, generally, right? Like if you see a movie of a wheel that's filmed in such a fashion so that you, even though you know from the scene it's going this way, it looks like it's shuddering or standing still or going backwards or whatever. Everybody sees that, right? Everybody sees that. Like, you don't see it differently from... So we're all picking the same way to T-interpolate. What way do we pick? We pick that way. We pick the special way. Why? I don't know. That's a cognitive science question. Why do people come up with the lowest bandwidth explanation for what they see in the movie? I don't know the answer to that question. Do you? I think it's an interesting question. So let me pose it and see if you guys can... Ricardo? I don't know that either. You know, like Bruce Land might know. He knows everything like that.
Well, it depends.
Remember, eyes aren't the only...
Right. But for movies, like flashing, alternating between like white and black, you can see the flicker around 6. Like, but that's like the maximum, like from bright white to pitch black. In a movie, you don't even notice it because so many of the frames are really similar.
Okay, well, actually, let's pick it up next time. I just want to go through one example of this, and then you can ponder the following question. Like, did I talk about the cochlea being a spectrum analyzer? How? Oh, yeah. Last year, not this year, though, right? Yeah. Okay. So anyway, one of my pet theories is that we're sort of condemned physiologically to think of the world in terms of frequency, because our ears are spectrum analyzers, and so we had to discover Fourier analysis, right? Our ears don't do wavelet decompositions of sounds. You know, they do Fourier decompositions of sound. And so we have to think in terms of bandwidth. Our brains are wired to think about frequency content and bandwidth, and we look for low bandwidth explanations. I think that's a bogus argument, but it might be true. You know? So we'll talk about that next time.